Uh, Bismillah ar-Rahman ar-Rahim. This is chapter 2, which is about harmonic overview, harmonic distortion and definition. So we're going to talk over here about the harmonic distortion, Fourier series representation, voltage versus current distortion, harmonic versus transient, power and power factors, displacement factors, tripling harmonic, harmonic sources, harmonic distortion evaluation. If we apply sinusoidal voltage waveform across a non-linear load such as non-linear resistor, then since it is non-linear resistor, that means the relationship between the voltage and the current will be non-linear. But because this resistor is not linear, then it will draw such kind of current waveform, which is distorted. It is not a pure sinusoidal waveform. And that will create, of course, harmonics. If we have any distorted waveform, such as what is shown over here, so based on the Fourier series representation, this distorted waveform can be written as fundamental component plus other harmonics. And normally if the waveform is in this shape, then normally we're going to have, mainly we're going to have the odd harmonics, odd. The value of the even harmonic will be negligible or very small. And this is the how can we write the waveform? So f of t will be equal to a DC component plus cosine component time an plus sine component time bn. This equation also can be rewritten as shown over here. C naught plus Cn cosine n omega t plus theta n. Harmonic of order h, we call it 1, 7, 13. We call, or they have positive sequence based on this table. Because normally in any waveform we're going to have the first, second, third, fourth, fifth, sixth, seventh, and so on. And the phase sequence of the fundamental course will be positive, second negative, third will be zero sequence. Zero sequence, that means the current or the harmonic from different phases will have the same phase angle. So that's why we call it zero sequence. So positive, negative, zero, and so on. Then if you look at the positive, it will be first, fourth, seventh, and so on. The negative sequence will be the second, 5th, 11th, and so on. And those are generally the zero sequence, which is the tripling. Third, of course, there is the zero sequence are anything multiplied by 3. Any integer you multiply by 3. So the third, 3 times 1, 3 times 2, and so on. But the tripling harmonic, what they call the tripling harmonic, mainly are the odd. Then it will be third, and then to be 9th, 15, and so on. The voltage that come from the generator are pure sinusoidal, because that will depend on the design of generator, and normally the generator are designed such that they will provide pure sinusoidal waveform, and the angle between those waveform will be 120. But now let us say that if we like to calculate the voltage over there, so the voltage over here will be the source voltage, which is sinusoidal, minus the voltage drop across the system impedance. Now the voltage drop across the system impedance, it is equal to current times Z. Now if the current is non-linear, if the current contains harmonic, so as a result the voltage over here will contains harmonic, since the voltage will depend on the impedance, right? So actually, because of the harmonics in the current, because of the non-linear load, that will create a harmonic voltage. And if you have distorted current, that will create also distorted voltage. Okay, if we have stiff power system, strong power system, normally we'll have very low impedance. So very low impedance, that means the voltage drop will be low. So as a result, there will be low voltage distortion, so we have no power quality issue. But if you have a weak power system, that means it will have high Z. High Z, that means there will be more voltage drop. As a result, there will be voltage distortion, and that will create power quality problems. What are the differences between the harmonic and transient? Transient waveform exhibit high frequency only briefly after disturbance, such as we said, we have the lightning that hit the overhead line, so the duration will be for a short period of time, but of course that will make a problem to the waveform. So transient dissipate within few cycles. Transient are associated with a change in the power system, such as lightning strikes, such as switching of the capacitor bank. Whereas if we look at the harmonic phenomena, they are always in the system. So it's happened during even the steady state. And of course the harmonics will be multiple integer of the fundamental frequency. So if the fundamental frequency is 50, then 2 times 50, 3 times 50, that will give us the harmonics frequency. Continuous waveform, or at least for several seconds. So those harmonics will be continuous, or it will stay for a long period of time. It depends on how the load behaves. Harmonic are associated with the continuous operation of the load. If we have pure sinusoidal waveform, so we know that to find the apparent power will be V root mean square times I root mean square, or the S. The apparent power can be calculated from P square plus Q square. Real power will be S times cosine, right? S, which is IV. Q will be S sine, and S is V times I. And power factor will be the angle between the S and P, or the angle between voltage and current, since the current will be over here in phase with the power, and the voltage will be over here. Okay, so the angle between V and I, or between P and S, will that will give the power, the angle of the cosine or the power factor. This is if we have pure sinusoidal waveform. But if we have a waveform that contains harmonics, then we have to use another equation, of course, because we have to take the effect of the harmonics in the waveform. Okay, so therefore to calculate the average power, so we need to consider all harmonics present in the system. So that's why we said that the average power will be equal to V root mean square K, I root mean square K, and K will represent the harmonic order. Cosine the angle between the voltage and current. Then we have to take the summation of those. So that will give us the power, the average power. Because the voltage distortion is generally low and it is less than 5%, then we can do some approximation, so in which we can say that power average will depend on the fundamental component. Same thing will be with the reactive power. So this is the general formula. Then again, because the voltage distortion is normally small, then it can be calculated from the fundamental component of the voltage and the current, sine the angle. S, now what will be the apparent power? Of course, the general equation for the apparent power will be the V root mean square times I root mean square. But over here, again, we need to consider the effect of all harmonics. So then we have to have over here another factor. This factor is called distortion volt ampere, or distortion power. And that represents the additional contribution to the apparent power by the harmonic. So since this harmonic will come from a source, right? So now your main source will consist of fundamental and harmonic. So that's why S will contain that additional source, which is called distortion power. So if we like to calculate what we call it the displacement power factor, so it is the angle between the fundamental component of the voltage and the current between V1 root mean square, I1 root mean square, so that will be cosine theta 1. But since the waveform contains harmonics, so we have also another definition which we call it true power factor, and that will be the angle between average power and apparent power. So the true power factor indicates how large the power delivery system must be built to supply a given load, right? So since S will be equal to P divided by the true power factor. So if true power factor is very low, that means we need to have a system that will give us huge amount of power, so that we're gonna satisfy our real power requirement. On a typical system, the I root mean square term given in the true power factor is generally the one most affected by harmonic distortion, although the V root mean square may also be increased. Now let us assume that the voltage total harmonic distortion is 0, so no distortion in the voltage. Then we can find the equation for the true power factor. So this is the general equation for the true power factor, P over S. And now we can do approximation. P is equal to P1, okay, where P1 will be the fundamental component of the voltage and the current cosine the angle between the two fundamental components, divided by S. Now let us assume that there is no voltage distortion, we have only current distortion. So then V root mean square will be equal to V1, then V1 will cancel with V1. Then we're going to end up with that P true power factor will be equal to I1 cosine over I root mean square. Okay, then the maximum power factor true will be 1 cosine phi is equal to 1. Therefore 1 cosine phi is equal to 1. The true power factor will be equal to I1 over I root mean square, and I1 over I root mean square also can be written as 1 over square root of 1 plus total harmonic distortion square. And this one can be obtained, of course, from here. There is the simple proof. So we have total harmonic distortion for the current. Well, as you know that it will be the square root of the I harmonic current. If I'm consider only now the odd harmonic, so I3 square plus I5 okay, so let me take this H. So since H will be those numbers, so I3 square plus I5 square plus I7 square plus blah blah blah, okay, divided by the fundamental current, the root mean square of the fundamental current, right? Now if we take all those harmonics, I3 square, so the root mean square of the third harmonic, the root mean square of the fifth, and so on. So those also can be written as the total root mean square current, the total current minus the fundamental, right? Minus fundamental current. Since the total root mean square current will be equal to the fundamental plus all the harmonic divided by I1 square. So that will be the total harmonic distortion for the current. Now if we take the square for both sides, then total harmonic distortion square will be equal to I root mean square minus I1 square divided by I1 square, right? Then if you find I1 in terms of I root mean square, so we can just say that I1 square times total harmonic, I1 times total harmonic distortion square, this is the okay, equal to I root mean square minus I1 square. Take this one to be there, okay, then you will end up with, you will take I1 as a common, I1 square as a common, then you will end up with total harmonic distortion square plus 1. So that will be equal to I root mean square. Therefore I1 over I root mean square will be equal to, of course, this one plus 1, okay, I forget the 1 plus 1, okay, it is already there, okay. So therefore I1 over I root mean square will be equal to 1 over total harmonic distortion square plus 1. Okay, then if we take the square, it will be under the square root as it is written over here. Okay. Okay, so the maximum true power factor will be equal to 1 plus 1 over the root square of 1 plus total harmonic distortion square. Therefore, as the total harmonic distortion goes up, of course, the true power factor will go up. Will go down. Okay. Harmonic distortion result in additional current component following in the system that do not yield any net energy except those who will cause losses in power system. For example, in electrical machine that takes those harmonic, it will cause overheating to the electrical machine, and also it will cause mechanical oscillation due to the pulsating torque, because you will not have smooth torque. Now the torque, because you have harmonics, the torque will not be smooth, so it will cause torque pulsation. This will require the system to be built at slightly larger capacity to deliver the same power to the load. So don't forget that the load need a certain power. Now part of this power will be utilized to supply the harmonic. Therefore, to provide the same real power, S should go up. Okay. And this factor, D, due to the harmonic, can be, of course, calculated from this equation. Okay, again, this is the definition of the triple harmonic. So they are odd multiple of third harmonic. What are the problem of the tripling harmonic? Suppose that over here we have a load that takes three phase. We have three-phase load that takes energy from the source, and the current waveform that taken by the load contain the third harmonic. Of course, don't forget that the third harmonic, that flow will be in phase. Okay, so for phase A, this is for phase B, and this is for phase C. So all the third harmonic will be in phase. Then of course, if you add those, then the result will be 3 times I3, right? If the system is balanced, the total current that goes to the neutral will be 0 if the system is balanced. But because we have harmonics, and the third harmonics, of course, will have the different third harmonic that flow through the different phase are in phase, then the total current that goes through the neutral will be 3 times the third harmonic current. So that's why the neutral will be overloaded. The neutral is designed, let us say, to carry the normal current, but now there is more current flowing in the neutral, and that also will result in the distortion of the neutral voltage. As a result, device misoperation. It will cause also telephone interference. So those are the problem of the harmonics, or of the third harmonic. So over here, just I'm going to show how the third harmonic will be generated in different phases, and as it is clear that they will be in phase. Okay, so the third harmonic current are in phase. How to get rid of the third harmonic? I mean, such that it will not affect the load. Well, if over here we have a certain load, then what we can do, we can just make the transformer connection to be delta. Then those third harmonic will not go to the load, will not, or if this is our source, they will not be injected back to the source. They will keep circulating in the delta connection of the transformer. They will not go out. Again, just from the Kirchhoff current law, right? So over here we have a third harmonic, over there we have a third harmonic. So the current that enter will be equal to the current that leave, right? Then nothing will go there. So the tripling harmonic current remain trapped in the delta connection and will not show up in the line current on the delta side. Of course, if we make those kind of connection, for example, YY, and the Y is connected to the ground from the neutral, so the third harmonic component will circulate through both. What are the harmonic source? So we said that non-linear load, such as separable transformer or non-linear resistor, electronic device, and arcing device. Of course, I mean, arcing device, we can have the arc furnace that used to melt the steel, or the light that we are using. If we are using, let us say, fluorescent light, they are based on the on arcing. So they have what we call it, they have ballast that will cause arcing, and as a result the light will be on. If we look at the suitable device such as the transformer, so normally the transformer, to be more efficient, to have effective cost, it is designed to work just near the knee, just below the knee. This is how they design the transformer, because we like to make optimization of the cost and of course other factors. So the transformer and also electrical machine are designed to work somewhere over here. But now, if we look at the current that will be taken by the transformer, with the transformer will take a current that will be given to the secondary, or that will be provided to the load, but also it will create its magnetization as well. So it will take what we call it a magnetization current, and that current will depend on the applied voltage, right? So the if we look at the what we call it the pH curve, or the voltage against the current characteristics. So over here we apply a certain voltage to the transformer that will create certain flux density. So as a result, that will give a certain magnetization current. So if we look at this green curve over here, so that green curve will give this kind of magnetization current. But as the voltage goes up of the primary, as the voltage goes up, the flux will go up. As a result, look now at what will happen to the magnetization current. It will take this shape. Okay. It will take this shape. So as a result, it will have third harmonic. And this is how the how the transformer magnetization current look like. If we do Fourier analysis for this current, this is the result. So you see that we have fundamental component, we have a third harmonic, you see that 60 times 3 will be 180. We have fifth harmonic, but the larger part, or the dominant part, will be the third harmonic. So some other example of the saturable device is the saturation of magnetic ballast in the fluorescent lamp. So the amount of the third harmonic current is ranging between 15 to 30%, and this is how the current that is taking. So it is very clear that there is a kind of, see that there is kind of harmonics exist in the current that is taken by the fluorescent lamp due to the use of the magnetic ballast. This is how the fluorescent lamp look like, and the ballast, it can be either magnetic ballast, which look like that, or it can be electronic ballast that look like that, and that will have this circuit over here. Of course, the ballast is a device used with a gas discharge lamp to provide the necessarily starting and operating electrical condition. But anyhow, because they are using those kind of lamp, then that will create also a third harmonic. Those are also some of the harmonic source that come from the electronic device. So we can have harmonic source coming from the switch mode power supply. Of course, you know that switch mode power supplies are used nowadays in most of the electronic equipment, such as computers, photocopy machine, the printers, scanners. They are using mobile, so they are using switch mode power supply. Voltage source converter, which is used to provide energy to the adjustable speed DC motor drive. PWM converter, which is used to provide the energy to the AC motor. And of course, we know that we have already talked about the electronic ballast. So this is also an electronic device that is used to provide the required switching mechanism for the fluorescent lamp. Battery charger. So those are only some, of course. So only some type of electronic device that will create harmonics. Okay, now if we look at single phase power supply, so we can have switch mode technology, which is the current technology that are used to provide the required energy to our mobile, to our printer, to our computer. All the AC voltage control technology, and this is the old technology. This is now it has very limited use since it is a bulky device. It will cause more losses. It is more expensive compared with this one. So nowadays they are using switched mode technology instead of AC voltage control technology. And this is the simple circuit for the switch mode power supply. So suppose that you like to charge or to place or to provide energy to your computer. Of course, inside this device. So this device we call it switch mode power supply, and actually it consists of this circuit. So since you are plugging the wire to the AC, so in Oman, of course, our AC is 240 volt single phase. We're gonna have a rectifier over here, double rectifier. Then you have a capacitor bank, just to smooth the DC voltage. Then over here you have another controller over there that will provide again controlled AC voltage. Then you are using a very small transformer that will have very high efficiency. Then a rectifier again to provide the required DC to your PC. So we're gonna have smooth DC output. In general, it is lightweight compared with the bulky construction of the AC voltage control. It has compact size, efficient operation, toleration of large variation in the input voltage. So and it can be used, of course, for phone charger, for the computer, printer, photocopier machine, and so on. This is the current that is taken by the switch mode power supply. So you can see that it contains a lot of harmonic. Now if we do Fourier analysis, this one will be the result. So you can see that we have third harmonic 65.7%, fifth harmonic 7th, and so on. We have also, if you look at the even harmonic, they are negligible, 0.2%, 0.4%, 0.4%, and so on. So that's why if we have such kind of waveform, then mainly we're going to have only odd harmonic. So the third, the fifth, the 7th, the 9th, 11th, and so on. As we go down, the percentage of those harmonic will go down. So the current taken by the switch mode power supply will be short pulses, as we can see it from this figure. Okay, the third harmonic, of course, component is the dominant one. It represents around 65%. It will overload the neutral conductor of a three-phase system. So we need to make sure that the neutral wire are really designed to carry this high current. it will cause transformer overheating under a significant switch mode power supply load. Then of course if we have, let us say, if we have a building that contains mainly computers, of course, I mean that building, let us say, it is used mainly to provide energy source to main electronic device, including computer and maybe others. So when we design that transformer, we need to make sure that the transformer will able to supply the required load. So since we know in advance that our load will be mainly electronics load, computers and so on, then we know that there will be a third harmonic. And we know that, I mean, the third harmonic will cause, of course, losses and problem. So then what we have to do, we need to derate that transformer. So if let us say that the required load that needed by those computer will be 1000 volt ampere, then we have to choose not 1000 volt ampere. We have to choose a transformer that will have a bigger size, or in other words, we have to, what we call it, to derate the transformer. So if if our transformer that we have selected is 1000 volt ampere, then we need to make sure that actually this transformer is supposed to work only 80% of 1000. It should not work at 1000 megavolt ampere, because that will reduce the lifetime of the transformer due to the losses that will be created by those harmonics. So then if we selected 1000 volt ampere transformer, it has to be run at only 80% of 1000. So that means our load, it's supposed to not exceed 80% of 1000, which is 800 kilovolt ampere. So in other words, if our load is 800 kilovolt ampere, we need to select a transformer which is 20% more. Okay, this is again the current taken by the fluorescent lamp, because the fluorescent lamp use either the magnetic ballast or electronic ballast. Then there will be, of course, very high distortion in the waveform, and this is how the current look like, and the total harmonic distortion for the current will even reach around 100%. Okay, this is the three-phase power converter, which is used to provide energy to the DC motor. So of course over here we have a rectifier, which can be in which we can utilize diodes, or if we like to control the voltage, we have to use a thyristor. This one, it will offer wider speed range and higher starting torque. Purchase and maintenance cost of DC motor are high, of course. DC drive are limited to the application that require wide speed range and high starting torque. The two largest harmonic current that will result if we provide energy to the DC motor by using polytronics will be mainly the 5th and the 7th. If we have very large motor, then in that case, to reduce the harmonic, it will be better to use what we call a 12 pulse rectifier. Those will be 6 pulse. We have 6 devices that will create 6 pulse. So I guess we have to use the 12 pulse, and that will reduce the amount of the harmonic. This is how the voltage will look like. For AC motor, of course, AC motor, it needs AC source, And now if we provide the AC source from again from the variable AC source, in which we will use the electronics device, so we can use what we call it voltage source inverter. So we have AC source which are fixed, then we change those AC source to variable DC by using rectifier. We can use the resistor. Then we are putting filter to smooth the DC. Then we are inverting the DC to provide the required AC voltage for the motor, and this is how the voltage will look like. So we can use what we call it voltage source, or we can use current source inverter. In current source, we are using over here very large inductance, and that large inductance will provide almost a constant current to the inverter. Okay, we can also use what we call it the inverter that will be based on what we call it PWM, pulse width modulation. So those inverter that will convert the DC to variable AC, so those switches will be switched on by using PWM, pulse, we call it pulse width modulation. And again, what is the advantage of those? That will reduce the amount of the harmonics. Compare with this one, compare with those, with the 6 pulse or with the 12 pulse. You call it voltage source inverter PWM drive offer the best energy efficiency over a wide speed range. It is used for motor below 500 horsepower. AC waveform as a train of variable width pulses. So as you can see, so look at the voltage, how it look like. Those are the number of the switch that are used. So normally they are using IGBT nowadays, but also they can use BGT or GTO or SCR. And of course they are using diode break rectifier to convert the AC to DC. Okay, this is the waveform. This is the current waveform that will be taken by the voltage source inverter that are fed by using pulse width modulation. So look at the harmonics. No third harmonic, no triple harmonic, nothing. We have 5th harmonic, we have 7th harmonic, 11th, 13th. And total harmonic distortion is in this range, 40 to 60. If the motor are fed from PWM. Okay, also this is the current and harmonic spectrum for the current source inverter type for the DC motor drive. So if we are using current source inverter, again the third harmonic will be almost negligible, and the total harmonic distortion will go to 30% for the current, of course. So this kind of shape, they call it a rapid air. Okay, we said that we have also arcing device that also will cause harmonic, and those arcing device can be in several places. Can be in arc furnace. So what is the use of the arc furnace? Arc furnace are used in steel industry to melt the steel. Arc welder, it is used to weld the steel. So all of them are based on arc. And also in the discharge device, the light that is utilized, such as in fluorescent. We said that we have two types of ballast. So we can have magnetic ballast and we can have electronic ballast. So the light will be generated by sending electric discharge through ionized gas. Okay, so this is the idea of the fluorescent light. Okay, so again, those are nonlinear devices. And even if we look at other type of light, it is not only fluorescent but also sodium vapor are based on the same principle also. Mercury vapor is based on the same principle, in which the electric discharge will be sent through ionized gas. Now, how to do harmonic evaluation? So harmonic current produced by nonlinear load can interact with the utility supply system, as we said, right? As we said that the voltage will be equal to I times Z. The voltage that comes from the generator it is sinusoidal, of course, but because the load generates harmonics, that means the voltage at other point in the power system will contain also harmonic. So the interaction often gives rise to a voltage and current harmonic distortion that can be found in many places in the system. Therefore, to limit both the voltage and the current harmonic distortion, then IEEE came up with a standard. They call it IEEE 519, that was published in 1992, and that proposed to limit the harmonic current injection from the end user, so that the harmonic voltage on the system will be acceptable. Okay, so this approach requires participation from both, from the end user as well as from the utility. They came up with two indices. Total harmonic distortion, as we have discussed it already in chapter 1, and also total demand distortion. Both are measure of the effective value of a waveform and may be applied to either voltage or current. So the end user and utility share the responsibility for limiting the harmonic current injection and the voltage distortion at the point of common coupling. I will talk about what we mean by BCC. What is the point of common coupling? So since there are two parties involved in limiting the harmonic distortion, the evaluation of harmonic distortion will be divided into two parts. So the first part, measurement of the current that are injected by the load. Then we need to also to calculate the frequency response. So that means we need to plot the system impedance response with respect to the frequency. This is very important. System with respect to the frequency. Why is that? Because resonance can happen. Resonance can occur in the system. And of course, if the resonance occur in the system, that can do a disaster. So we need to make sure that there will be no resonance. So that's why we need to calculate the frequency response. Now, what we mean by point of common coupling? That means evaluation of harmonic distortion are usually performed at a point between the end user and the utility system. Okay, so suppose that over here we have a new customer, new large customer that need a transformer, and of course he will be connected to power system at this point. So this point is we call it a point of common coupling, where where another customer will be served, because if he generates harmonic, he will affect also the other customer. And over here again, this is the new customer, and those are the old customers, so he will be connected to there. So this is the point, what we call it, the point of common coupling. Okay, harmonic distortion evaluation, the utility. Since harmonic voltage distortion on the utility system arises from the interaction between distorted load current that come from the load, okay, and the utility system impedance, the utility is mainly responsible for limiting the voltage distortion at the point of common coupling. Why? Since other customer will be connected at that point. Okay, so you could have a customer that will generate huge harmonic, and you could have a customer that will not generate any harmonic. So if the utility does not take, I can say, an action, so the other customer will be affected. His equipment will be affected, although he's not generating harmonic. The limits are given for maximum individual harmonic component and for total harmonic distortion. So the utility need to make sure that the total harmonic distortion at the point of common coupling will be according to the standard, and also the individual harmonic that will be injected will be at the will be also limited according to the standard. For example, I will show you, of course, later on the IEEE standard, but they say that for a system, if you have a system that is below 69 kilovolt, then the total harmonic distortion should be less than 5%. So the total harmonic distortion for the voltage should be less than 5%. And of course, we have already talked about the total harmonic distortion, which we say that it is the summation of the individual harmonics starting from second divided by the fundamental component of the current or of the voltage. Of course, all those will be the root mean square value, okay? Let us look at this example over here. Okay, suppose that we have this table that contains harmonics from 1 to 19, and those are the amplitude of the different harmonics. And now we like to calculate the what will be the total harmonic distortion for the voltage. So it is just taking those number, plug it in the equation, and that will give us the result. Okay, so the total harmonic distortion for this one will be 32.48%. Okay, so this is the standard for the total harmonic distortion. Okay, so if the system voltage below 69 or equal, then the total harmonic distortion for the voltage, it has to be it should not exceed 5%, and the individual harmonic should not exceed 3%. Of course, as the voltage level goes up, the total harmonic distortion should go down. So this is the IEEE standard, and say that total harmonic distortion value on this table is expressed as a function of the nominal fundamental root mean square current rather than the fundamental frequency voltage magnitude at the time of the measurement. So we are using the nominal fundamental system voltage. For example, over here, V1 root mean square, if our system is at, let us say, at 69 kilovolt, because this is the line voltage, then V1 root mean square will be 69 divided by root 3. Okay, so the definition used over here allow the evaluation of the voltage distortion with respect to fixed limit rather than the limit that fluctuate with the system voltage. Of course, we're gonna do inshallah calculation later on to find the total harmonic distortion. Okay, and of course, I mean, same thing will be done by the current. And this is the okay, so we have total harmonic distortion for the voltage, we have total harmonic distortion for the current, and this is the equation that is used to find what we call it the total demand distortion. This is total demand distortion, and over here it is in terms of maximum demand load current with respect to maximum demand load current. Okay, so again, what we need to find the different harmonics, so the root mean square for the second harmonic, the third, and so on. Then we put them under the square root, divide that one by the maximum load current of the system, and that will give us what we call the total demand distortion. And this is the of course there will be also a table which is shown over here. So this is again the IEEE standard 519 1992 for the current distortion limit in percentage of the maximum current, and again it depends on the voltage that we are working with, and it depends on the ratio between the short circuit current and the current and the maximum current that flow in the system. So if we have a certain system, we have first of all to check the system voltage, then check the ratio between the short circuit current and the maximum current, and then we can determine what will be the total demand distortion. So those are the information that will be required. We need the magnitude of the individual harmonic component because of the equation again. We need to find the short circuit current at the point of common coupling, okay? And that one of course will be given, it's supposed to be given to us because that will depend on the system. And then IL will be the fundamental component of the maximum current at the point of the common coupling. And of course it can be calculated based on the average of the maximum monthly demand current in the system for the previous 12 months, and that is supposed to be given to us by the utility company. Okay, now how to determine the short circuit current. So those are the procedure that is used to determine the short circuit current. Determine the three-phase short circuit duty at the point of common coupling. This value may be obtained from the utility, okay? Because normally the utility will provide this value as megavolt ampere, and they call it short circuit megavolt ampere at the point of common coupling. Then we can find the current directly by dividing by taking the megavolt ampere and divide it by the line voltage. We divide it, of course, by the phase voltage, okay, by using this equation, and that will give us the short circuit current. Then we need to find the load average kilowatt demand over the most recent 12 months. Again, this one can be obtained from the utility. Then calculate the maximum current, root mean square current, from the equation of the power and power factor that also will be given to us. Then we can find the ratio between the short circuit and between the load current or maximum load current. Okay, let us look at this example over here. So in this example we have 3 single phase transformer. So the transformer is rated at 11, the single phase is rated at 100 kilovolt ampere. Okay, so we have a transformer. Okay, and it has this voltage level. This is 12.5 kilovolt at the source side. This is this is volt, this is kilovolt, this is volt, and the S for the transformer is given as the single phase 100 kilovolt ampere. Okay, with impedance of 2.6%. So the impedance of the transformer 2.6%, and it supply 200 horsepower, variable frequency drive. Fault current on the primary side is 900. So short circuit current over this side, so short circuit on the primary equal to 900, and short circuit on the secondary equal to 700 ampere. Okay, the utility was not specific to the location of the point of common coupling. Calculate the total demand distortion. So we like to calculate the total demand distortion at the primary side and at the secondary side. Okay. So of course, I mean, to calculate the total demand distortion, we need to find the ratio of the short circuit compared with the maximum load current. So we know that the short circuit on the primary side is 900, and the load current will be 8. Now how we obtain 8? We just we said that S is equal to V times I, and I will be equal to S divided by V, and this is a single phase, so S is equal to 100, and okay, and V is equal to on the primary side, so this is 100 kilovolt, and this is 12.5 kilovolt, 12.5 kilo. So if you divide 100 over 2.5, that will give you 8 ampere. So now we have the short circuit is 900, the voltage is 12.5, and that should give us the ratio as 112.5. Okay, so now from the table, if we look at the table, if we go back to the table over here, we look at the table, so we have I short circuit will be in this ring, therefore because it was 112, so the total distortion will be in this ring. Okay, so that will be around 15. This is if we choose the point of common coupling to be on the primary side. If we choose it on the secondary side, again the short circuit current is given. We need to find the load current again, so it will be S divided by the voltage 480, and that will be 208. Find the ratio, and then you will find that the total harmonic total demand distortion will be in the ring of 8%. Okay, a typical example for single phase distorting appliances are TV, receiver, personal computer, microwave. Of course, those are all single phase, and this is how the current will look like. Now, if we take the Fourier analysis, this one will be the result. So the main harmonic will be the third, the fifth, and the seventh. Okay, again, this is another example over here. So to say that what we have over here, we have office block that will have 1000 computer and 1000 kilovolt ampere transformer are used to supply the building. So over here we have transformer, and the size of the transformer is 1000 kilovolt ampere, 1000 kilovolt ampere, and this is 11 kilovolt, the primary side. Secondary side 440 volt. Of course, this is the three-phase. Then we can calculate the rated current in the primary and in the secondary. Of course, we are interested in the secondary, since this transformer will provide energy to that building, which contains 1000 PC. So the current will be equal to the S divided by V line or root 3, and that will be around 1300. Of course, over here in the question he said that assume that each computer will take a fundamental current of 1 ampere. So since we have 1000 computers, so now this transformer will provide 1000 ampere to 1000 computer. And also he told us that assume the following, that the third harmonic will be 72%, the fifth will be 60, seventh will be 40, ninth will be 2.6. So over here, of course, what we need to find what will be the total demand distortion. So we need to find the percentage of each harmonic, or no, we need to find the value of each harmonic. So this is the value of the third harmonic in one phase. So we have 1000 ampere, that will be the total current taken by 11 computer, and over here we are looking only at one phase, so divided by 3, right, time 0.72, which is the percentage of the third harmonic. So then the third harmonic current will be 240, and then the other can be calculated. Therefore, the total demand distortion will be equal to the summation of the different harmonics divided by the maximum current that will be taken from the source of the rated current, which is 1312, and that will give us, so the total demand distortion will be 26.5% for this building. Okay, crest factor, they define the crest factor as the ratio between the peak current to the root mean square current. So over here, if we have, let us say that we have a sinusoidal current with the a peak current of, let us say, it's written over here, around 7.7 ampere, and of course the root mean square will be 7.07 divided by root 2, that will be around 5. So the crest factor over here will be root 2. Now if we have a waveform which look like that contains a lot of harmonic, and still the root mean square value for the current will be 5, but in this case, of course, the peak current will be around 21.2, so the crest factor will be 4.24. So for the sinusoidal current, the crest factor is root 2, and for the non-sinusoidal, for the current which contains a lot of harmonic, that factor will jump to 4. There are two important components for limiting the voltage distortion on the utility system. So first of all, we need to find the harmonic current that are injected from individual loads, and that should be limited should be limited according to the IEEE standard, of course. So those users who will generate many harmonics, they suppose we need to make sure that the amount of the harmonic that they are producing is according to the standard. Otherwise, again, the other user will be affected. And the second point that we need to consider is that the overall voltage distortion level can be also high even if the harmonic current injection are within the limit. This condition occurs primarily when one of the harmonic current frequency is close to the system resonance. So this is another thing that we need to look at, a resonance problem. So we have let us say a user that will inject a lot of harmonic. He places a filter to reduce the harmonic. But if you place a filter to reduce the harmonic, that filter can cause another problem also to the system. It can cause resonance. So that's why we need to find, we need also to do a calculation of the impedance with respect to the frequency to say how the impedance of the system will look like with respect to the frequency. Harmonic distortion evaluation of the utility system, characterization of the harmonic. So we need to take measurement, and this measurement, it has to be done at least 1 week. So we need to bring our poor quality device connected at that point, at the point of common coupling, let us say, and then or at the user in which we are suspecting that there is a source of the harmonic that coming from this user. Keep it for 1 week so that all cyclic load variation can be captured by those devices. This is example of how the total harmonic distortion will look like over 1 week period. So from Monday to Sunday. So sometime the total harmonic distortion will go up, sometime it will be between 3% to less than 1.6%. So that's why we need to put it for at least 1 week, or this is the recommended duration, 1 week. Continuous measurement. Okay, the second thing that we need to do to do system modeling. Okay, again to see the different harmonics that may be injected in the system, to plot the system impedance against the frequency. All those should be also done. So of course system modeling, and then we have to look at the frequency response, which is the impedance against the frequency, because that can cause again harmonics. Placing filter can cause harmonics, so we need to check that whether the system impedance against the frequency will not be affected by the harmonic. And the also evaluation of the harmonic control scheme, which consists of controlling the harmonic injection from the nonlinear load. For example, if we have variable speed drive that are fed from, let us say, voltage source inverter, maybe it will be better to reduce the harmonic if we use PWM. Change the system frequency response characteristics. We find that there will be a possibility of resonance in the system. Then maybe we need to change. We need to relocate the filter. Maybe we need to relocate or to change the size of the capacitor bank that is used as a filter with the inductor. And maybe we need to block the flow of some harmonic also. because we can have a filter that will absorb both harmonic, and you can design a filter to prevent the flow of the harmonic. Okay, that's all. Thank you very much.